Well, good morning and good afternoon. Just going to give you a sketch in the next roughly 1 hour of some work that we've been doing with our international collaboration on trying to expose and explain the emergence of mass in the standard model. Except I can't change my slides now. There we go, that's good. So to begin, our universe is what it is, and its existence depends on a few simple facts. One of them is the proton is massive, and by that I simply mean that the mass scale for strong interactions is so very different to that of electromagnetism. Further, the proton is absolutely stable, and that's peculiar because the proton's a composite. It's made of 3 valence quarks, and in our experience, almost every composite object we know falls apart into its constituents. But that's not true of the proton. In the 14 billion year history of our universe, no proton has ever been seen to decay. And the lifetime of the proton in experiment is much larger than that. On the other hand, we have a pion. It's crucial to nuclear structures, the formation of everything, but it's unnaturally light. It's not massless, it has a muon-like mass, but it is very much lighter than the proton, and that's despite being made of much the same objects as constitute the proton, a valence quark and a valence antiquark. And these things are examples of emergence, low-level rules producing high-level phenomena with enormous apparent complexity. We imagine, as physicists, that we have a Lagrangian, a one-line Lagrangian, expressed in terms of gluon and quark partons. And these objects are not the degrees of freedom that are measured in detectors, and that makes QCD special. We have to understand what are the asymptotic detectable degrees of freedom, how they're built from the Lagrangian degrees of freedom, and also then is QCD really the theory of the strong interactions? And perhaps even, is QCD really a theory? Because that point, if it is really a theory, then we may have something to say about going beyond the standard model in new ways that we don't always talk about. What does well-defined mean as a quantum field theory? Well, one definition I've listed here, QCD has a finite number of renormalization constants that makes it possible. And these renormalization constants, if they can all be computed and remain bounded real numbers as any regularization scale is removed, then the theory is well defined. QED fails that test because the Landau pole exists in the ultraviolet. Weak interactions are essentially perturbative because we put the Higgs boson in there, and that is an enormous mass scale that suppresses infrared physics. But the Higgs boson mass itself is quadratically divergent. That makes the whole theory and the whole electroweak theory not renormalizable. So it's broken. On the other hand, we have non-perturbative QCD. And our understanding of that has come a long way in the past few years. It is beginning to look very much like QCD is humanity's first well-defined 4-dimensional quantum field theory. So it can stand alone as an internally consistent theory, a predictive tool, just as we've written it down, with nothing needing to be added. And the question we're asking, or one of them, is how did this picture develop? Where did it begin? And part of that story centers on QCD's running coupling. This is the image one sees in textbooks for QCD, a running coupling that falls rapidly as the interaction scale, energy scale increases. The question we've long asked is what's happening in the infrared, because that's where we are living. Now, from the very beginning of QCD, the notion of asymptotic freedom came with a flip side, the notion of infrared slavery. This is based on perturbative analyses, which place a Landau pole in QCD at around about 0.2 GeV all squared. This leads people, or has led people, to imagine that the running coupling might continue to increase to infinity as k squared, the energy scale, goes towards 0. And that was often, and is often still, interpreted as being synonymous with confinement. A linearly rising potential, some have argued, will come from such interaction. And the time now is to ask whether this notion is correct. Well, there have been big changes, as I mentioned, and their origins perhaps lie some 40 years ago in a paper written by John Michael Cornwell, Dynamical Mass Generation in Continuum Quantum Chromodynamics. It has over more than 1,000 citations, and it exploits the fact that QCD has gluon self interactions, and that even without matter fields, is enough to make an interacting quantum field theory. And what he proposed, and has come to be understood in the last 40 years, is that owing to strong self interactions, these gluon partons, in terms of which the QCD Lagrangian is expressed, become quasi-particles. And they're described by a mass function that is large at infrared momenta. And what I've illustrated here is lattice results, the points, for the gluon two-point function, and continuum results for that very same function. And evidently, they both agree. This scalar function characterizes the gluon two-point propagator, and it's finite at 0. And that means the gluon has a mass. And this evolution is characterizing the gluon mass function. This is truly mass from nothing. Those gluon partons, which were massless in the Lagrangian, because the theory is interacting, have become massive objects characterized by this running mass function. And this is a QCD fact. We've learned that over the last 40 years. Continuum theory and lattice simulations agree. The point now is, can we list an array of observables that can enable us to verify this theoretical fact about QCD? Today, we have a gluon mass function. I've illustrated by the blue curve here. Johannes last week would have spoken about this at some length. Cornwell showed us some 40 years ago that the mass of the gluon is roughly half a GeV. In the next 40 years, we've established with a very good level of accuracy that this mass is renormalization group invariant 0.43 plus or minus 0.01 GeV, roughly half the proton mass. It's a prediction in the sense that it's half the proton mass. And it follows that gluons with a wavelength greater than 1 over this scale are screened from interactions. And such screening eliminates the Landau pole from QCD. That enables an infrared completion of the theory. When you have that in mind, you can go back to a meeting we held in Trento at ECT Star some 8 years ago, bringing together mathematicians and physicists working on the notion of continuum Schwinger function methods. And from those days, we've developed the capacity to define and compute what is a unique Gellerman-Low charge for QCD. And that's what I've illustrated here. This is a parameter-free prediction based on the best we have from continuum and lattice. And it shows this process-independent running charge, running coupling, which matches perturbation theory in the ultraviolet, but saturates in the infrared. There is obviously no Landau pole. So the infrared slavery picture is not correct in QCD. What's happened, in fact, is that long wavelength modes of the gluons are decoupled from the theory. So once again, the theory has become effectively conformal in the far infrared. The data you see on this figure is the process-dependent effective charge defined from the Bjorkane sum rule. And there are good reasons, largely tied with the isovector nature of the Bjorkane sum rule, for these two charges to agree. And so in effect, the process-independent charge is tightly linked to the process-dependent charge from the Bjorkane sum rule. And these things are discussed in some detail in a few references I've listed at the page here. These running masses are also transmitted into the matter sector. We have illustrated here, this is a picture drawn by Daniele, the quark mass function in the chiral limits, the up, strange, charm, and bottom quarks. You can see that in the chiral limit, there is a non-zero running mass for the quark. If perturbation theory were all we had, then this mass function would be identically zero. Evidently, it's not. And that's driven by the same effects that lead to a mass in the gluon sector. We have a point where this non-perturbative physics separates from the perturbative running of the quark mass function. And that's defining the onset of the perturbative domain. And that's roughly around about 4 times the proton mass squared. So you see above and below this transition domain into the far infrared. And when you go to the strange quark, you see that the Higgs boson mass, which dominates in the ultraviolet, is being overwhelmed by the emergent mass in the quark sector in the far infrared. And that gives us a chance to see how strange quark physics can provide us information on the interference between Higgs boson effects and emergent hadron mass in the strong interaction.
Craig, if I can ask a question.
Yeah,
so,
sure.
I was actually thinking about it, the gluon mass, as you mentioned it, like half of the proton mass. But the gluon mass would also be there in pure SU3 gauge theory, I imagine. So lambda QCD would be, in a way, a better measure of what it is. But you're right on this slide, obviously, that lambda QCD is more a theoretical concept, whereas a proton mass is more phenomenologically clear what it is, obviously, yeah.
Yes, I think there's a deeper point to what you're saying there, and that's what I was skipping over. Truly, we don't know what the scale is for nature. This is something that is not within the standard model. So when I said it's a prediction in the sense that it's half the proton mass, what I was driving at is that we need some empirical mass scale to define what we mean by the natural size of emergent hadron mass.
So that's the scale. It's just a scale in physical units, really. Then
that's right. So if I didn't know I had a proton, if I ignored matter fields, I really wouldn't know how to put bounds on the scales that QCD is generating, and I wouldn't really know if this theory was describing a nature that I could explore. So that's more than I'm able to answer right now. There is the potential for asymptotically free theories to have this emergent mass. Whether they do or not depends on an array of things, and one of them is what physics is actually relevant to that class of theories.
Mm-hmm. Okay, cheers.
So that is saying something that Feynman Mothersbaugh also said, is that all mass is interaction. And there's another point, the flip side of that is that often the absence of mass is also the result of interaction. So these are the emergent hadron mass basics. In the absence of a Higgs boson coupling, the Lagrangian of QCD is scale invariant. Yet massless bosons become massive. A momentum-dependent scale expressing a charge is introduced, and massless quarks become massive. And what these basic blocks tell us is that emergent hadron mass is expressed in every strong interaction observable. That's a great chance and a challenge for theory, because it gives us an opportunity to elucidate every observable consequence of these phenomena and highlight the paths towards measuring them. That makes all the facilities we build the tools for which we can expose emergent hadron mass. And then the challenge for experiment is to test these predictions so that we can finally draw the boundaries of what we really mean by the standard model and whether QCD is this internally consistent theory that I'm suggesting it to be. In this picture, we have the notion that the Higgs boson is critical to the evolution of the universe, but so far as the proton is concerned, it's responsible for just 1% of the visible mass, this small gray wedge here. The bulk of the mass of the proton, this 94%, comes from emergent hadron mass, all these effects from the gluon sector and the matter sector. And the remaining 5% is interference between explicit Higgs boson effects and emergent hadron mass. In quantitative terms, for a theorist, this is the nucleon or proton sigma term, which measures a product or interference between Higgs and emergent hadron mass. There are other systems to consider, and I've illustrated them here, the Pion and the Kaon. And they're special because if I turn off the Higgs boson, then these both are massless particles. We have connections between all of these pieces of physics, gluon and quark confinement, dynamical chiral breaking, and the Nambu-Goldstone modes, the Pion and the K. What we'd like to know is how the mass generating mechanisms in the standard model interfere to produce the physics we see. What's the role of the Higgs in this physics? Well, if I turned off the Higgs, as I said, the Pion and the Kaon would be indistinguishable. So the only differences between these two states come from the Higgs boson, giving the mass to the strange quark, which is much more than that for the up and down quarks. What is then the mass, and how can we unfold its expressions in all of the physics that we see? There's a basic feature that is well known, but often overlooked. If I take the Higgs boson coupling to 0, the pion exists and it's massless. And what's happening there is that emergent hadron mass demands an equivalence between the one-body mass in the dressed quark mass function and the two-body wave function of the pion. And this is nature's most fundamental expression of the Goldstone theorem. This identity between the two-body problem and the one-body problem is extraordinary. And it's only possible in quantum field theory with dynamically broken chiral symmetry. And what it's saying is that enigmatically, the properties of the nearly massless pion are the cleanest expression of the generation dynamically of mass in the matter sector. And that gives us a window, a very direct path to exposing some of the physics of emergent hadron mass, as I'll explain as we go along. It's possible now, after 100 years, to begin imagining using Meson targets, and so exploiting this identity between the one-body problem and the two-body problem. JLab, an electron-ion collider in China, they can use high luminosity electron and ion beams to access meson targets, pions and even kaons, through the so-called Sullivan process, tuning the kinematics so that this off-shell pion is nearly on-shell, and it can be kicked on-shell by interaction with the photon probe to make an elastic process or pseudo-elastic process or a deep inelastic scattering process, tagged deep inelastic scattering. This gives us access to form factors, and this gives us access to structure functions. The other handle is the fixed target program at CERN SPS, the AMBER proposal. Phase 1 has been approved. That will give us beams of 10 million pions a second. And in phase 2, for which the proposal is being prepared, we'll have 5 million kaons per second. And these beams, projectiles, give us what is effectively a pion or kaon target through the Drell-Yan reaction. And JPSI and prompt photon production can give us access to the gluon content, which makes this AMBER project quite unique. And this sketch shows us the relative luminosities and energy reach of the various facilities. JLab is high luminosity, but lower energy. EICC and AMBER overlap, and they form a very nice bridge between JLab and the proposed and EIC. So this landscape will give us a way of charting, finally, the structure of mesons, which is so important to the stability of matter today. Some of the things we can do and highlight are hadron radii. This is an interesting thing because a range of measurements can be made. Pion charge, kaon charge radii are extremely poorly known. And the reason you want to know them is because hadron masses and radii are a direct expression of the connections, links between emergent hadron mass and confinement. These two figures show continuum and lattice results for the product of the leptonic decay constant and the charge radius for a pseudoscalar meson, which is roughly constant, and the radius and the mass. The radius is 1 over the mass of the object, and you can see how good that is from both continuum and lattice studies. These things together tell you that leptonic decay constants and equally the charge radius are order parameters for emergent hadron mass. And that means that precise measurements of pion and kaon radii can reveal the compositeness or the confinement scales for Nambu-Goldstone bosons. Now, most people you ask would think that we know the radii of pions and kaons after 70 years, but that's not true. Our knowledge is actually very limited. The pion charge radius is poorly known. While the mass of the pion is known to 1 part in a million, the pion charge radius is constrained to only 1%, and even that's debatable. The most precise data is 30 years old, and they don't reach to very low momentum transfers. The most recent data is from Fermilab, but its errors are more than 10 times larger than those at CERN. And so far as the kaon goes, that radius is practically unknown. There are just 15 imprecise points measured on q squared greater than 0.015 GeV squared. And what we have shown using the slashing a point method that Daniele has perfected is that there's no information in here that you wouldn't get from a least squares fit. So 60 years of electron-proton scattering measurements analyzed by just fitting such data have shown us that that's no way to measure a radius. When we tried that with the proton radius, we ended up with the proton radius puzzle. These new methods enable us to extract, for the first time, a model-independent statement about the radius of Hadron. What we've found in analyzing the Pion is that there's a 2.4 sigma tension with the particle data group's most recent analysis. And there's, as I said, no information beyond the least squares fit in this kaon data. That sort of analysis has prompted, motivated the AMBER collaboration to explore what they might do with high-intensity Pion and kaon beams. They are capable of delivering precise data in this domain, sketched here, and that would be sufficient to enable the first objective extraction of the kaon size, a big step forward. There are many things I could talk about, but I think Parton distribution functions are helpful to expose a number of special issues in contemporary strong interaction physics. Some physics goals: we would like to have precise data that can be used to determine the distribution functions inside the Pion and the kaon, valence quark, C quark, and glue distributions. That would let us provide the first complete charts of the internal structure of these most fundamental Nambu-Goldstone bosons. Remember, quarks were discovered at SLAC in the late 60s, and we've been pursuing proton structure in this way since that time for 50 years. We tried with the Pion more than 40 years ago. That data only covers the valence quark domain. There's a 40-year controversy with doubts persisting over whether QCD actually agrees with the data or not. And regarding the kaon, there are only 8 points of data worldwide in this 40-year period. In the future, as I noted, Pion and kaon studies using the Sullivan process can give us electromagnetic form factors at large q squared. That will test the hard scattering predictions that we're familiar with from the late 70s. And also the distribution functions on the valence quarks at large Bjorkane X. The AMBER project will give us precision data for valence and C and glue. And the glue is particularly important because some people still claim that the Pion contains almost no glue. That would be peculiar, and our calculations do not support it, but these are still in people's minds, these notions. What I'm showing here is the most modern results from continuum in blue and lattice in gray. These techniques have both evolved to the point where they can provide point-wise predictions for distribution functions. And this confluence between continuum and lattice and reanalyses of data are showing us that we've made real strides towards understanding the valence quark structure of the Pion. And from some perspectives, it makes the standard model prediction stronger than ever before. So after 30 years, we are showing that an era is dawning where we can start to map out the internal structure of these Nambu-Goldstone bosons.
Greg, can I ask another question?
Yeah, sure.
So obviously you show on the slides that they exist, but just a very naive question because I don't actually know how these distribution functions are defined. So is it clearly defined to define valence, glue, and C distributions, so to say, or do they mix? You know, depending on, obviously they're probably gauge independent because you show lattice results here at your gauge independent. So, but are they clearly defined as separate objects, so to say? Yeah.
Yes, the valence distribution is a non-singlet distribution, so it's very clearly defined. The C comes from the singlet distribution, and that's just the total distribution of quarks minus the valence. So that's unambiguous. And glue, of course, is completely separate. What does happen is through evolution, valence quark produces C and glue, and then C and glue produce valence quark, and so forth. There's an interplay through the evolution equations. So these distribution functions evolve and depend on scale. And that's why when I've quoted them here, I've listed a scale, and zeta 5 means, in this case, 5.2 GeV. You'll see these functions changing in shape as one goes from smaller to larger scales. And that's simply saying that evolution suppresses the valence quark distribution and enhances both C and glue. There's no question about the definition, and there's no question about how one feeds into another. The calculation becomes difficult for many reasons, as you'll be familiar. If you're stuck with moments using a lattice simulations, the violation of rotational invariance makes it hard to get moments above 3. That's why these new techniques, there are 3 or 4 various techniques at the moment being explored to try and extract the pointwise behavior of distribution functions using lattice methods. This particular result was made using the notion of good lattice cross sections. So in a sense, it's similar to the experiment itself, where there's an inverse problem being solved to extract the distribution function. In the continuum, you have to make sure that you're using a symmetry preserving representation of the scattering process. If you don't, you can make a real mess of the calculations. So there are subtleties, and it's taken us 40 years to reach the point that these things are agreeing.
Okay, thanks.
The new part, very new, is that we're now reaching the point where we have predictions from the continuum and also lattice now for the glue and the C. And what they're exposing is that phenomenology or the global fits are not agreeing with predictions. Here is the continuum prediction, which matches the lattice. And here is one popular or modern contemporary fit to data for the Pion. You see, they're very different. The fit is much harder than the prediction. For the glue and the C, a similar thing is true. The glue prediction is much stronger in the infrared than the fit. And the same thing is true for the C. So we're having a real difference now. We're having a real chance to see whether global fits are valid or reliable in these domains. And that's the big step forward. If breaking news is that some lattice simulations are now making it possible to get gluon distributions as well. And this one from Hui Wen and Zhou Yu have produced for us the gray bands here, the gluon distribution inside the Pion. The green is the continuum, the gray band is the continuum, and the green is the lattice result. And you can see that these curves also agree. There is a big, larger error for the glue distributions at large X, but in comparing these, they're both very different to the phenomenological fits, which lie right down here. So the progress is being made. We are reaching the point where quantitative predictions from very different methods are beginning to agree on the distribution functions. And on the other side, because physics is an empirical science, we can anticipate that Amber at CERN can provide the data to test these theory predictions. Regarding the kaon, there's very little empirical information. We have valence quark distributions, results from models, and a single recent lattice study. And so far as the gluon C distributions are concerned, there are no results, or there were no results until recently. But in the meantime, looking at the valence part, this is the continuum result, the purple band, and the lattice result from MSU. Again, for this ratio of the U quark in the kaon to the U quark in the pion, there is good agreement. But the problem is here that because you're taking a ratio, uncertainties in both cancel. And so even though this ratio is a good comparison, if I took the individual results for the distribution functions for U in K and U in pi, then the continuum and lattice results will be quite different. What we need is new precise data on the distribution functions independently so that we can separate these. And this highlights something else. Just count these points. There are only 8. In the history of science, we've only managed to extract 8 points relevant to the distribution function of valence quarks in the kaon. We need to do a lot better before we can claim any understanding of kaon structure. The C, now again, we have continuum predictions for the glue in the C and the kaon. And we can start to address a big issue. Is there glue in the pion? Obviously, yes. And how is the glue in the pion different to that in the kaon? And that's what this ratio is showing. At small x, the ratio is 1 because glue and C are overwhelmingly dominant there. But in the valence region, where there is feedback through the evolution equations between glue, C, and valence quarks, the ratios differ. You see that in the kaon, the number of gluons is smaller at large x than in the pion, and the same in the C. These differences, which are as large as a factor of 30 or 40%, can be tested in experiments that will be done at amber. So this is the summary there. The distribution functions are similar to those in the pion when we consider the kaon. A detailed comparison requires the use of mass-dependent splitting functions. And we have some real predictions for the differences between these distributions that can be tested in experiments that will take place in the next 5 years, and then again in phase 2 after the next long shutdown at CERN. Mesons are easy in a sense for theory to do. Baryons are much harder, being at least a 3-body problem. And the way we can approach that in the continuum is to study the Faddeev equation. Introduced, what's that, 60 years ago, Faddeev showed that you can formulate the problem so that it has a unique solution. This was done in the context of quantum mechanics using pairwise potentials. We're dealing with a quantum field theory, so that must be generalized. And that was first done about 40 years ago, 30, I should say. You treat the 3 valence quark problem as a problem in quantum field theory where you preserve Poincare covariance. And that makes it possible to deal with the Faddeev equation for QCD-like systems. And this is highlighted in an extensive review by Guénot and his friends, and in a little shorter article by Xu. One of the things that Xu has shown us is how to produce a spectrum for the baryons. He's calculated a spectrum of ground state, J equals a half and 3/2 plus systems for all quarks, U, D, S, C, and B, their first positive parity excitations and their parity partners. And this is the sort of spectrum you can get, or you do get. We have lattice being blue, we have continuum being red, and we have PDG being gray. There's perfect agreement along the whole array. In this difference here, you see that the continuum studies did not include isospin or SU3 flavor breaking, and that's why you miss out a bit there. Beyond that, then Xu took this to make predictions for a range of 90 states not yet seen empirically. And this was quite a feat. This is a full solution of the 3-body problem in the leading order truncation of the Schwinger function equations. That's hard. You can simplify the problem by taking advantage of the features of quark-quark interactions in QCD that generate Diquarks correlations. This 3-body equation sums all possible exchanges and interactions that can take place between 3 dressed quarks. And as I mentioned, there are 3 or 4 people in the world today who can solve the Faddeev equation directly in this form. But owing to emergent hadron mass, there are strong Diquarks correlations within all baryons. The proton and the neutron contain scalar and accepted Diquarks. Others are possible, but they're not favored in these systems for dynamical reasons. When you capitalize on this, you can reduce the 3-body problem to an effective 2-body problem where the Diquarks form, but they're dynamical. They're non-point-like. It breaks up, joins this quark to form another Diquark, and so forth ad infinitum. And these Diquarks are non-point-like. They have sizes which are actually much like meson sizes. So they have soft form factors. They're soft correlations within the proton. This was explored a couple of years ago at a workshop at ECT Star. And from that workshop, a volume was developed about Diquarks correlations, their origin, their impacts in the experiment, and the empirical evidence. The question was asked is how firmly founded are these predictions of Diquarks correlations? The Beta-Salpeter equation reveals that strong correlations exist in all quark-quark scattering channels. Those familiar with the chat about diquarks might think of this tale of the good diquark and the bad diquark. Well, from a physics perspective, there's no such thing as a bad diquark. There are diquarks that are more massive, but they are all formed. They're all there. Using the continuum approach, the three-valence quark bound state problem, you can see how diquark correlation will emerge from the three-body problem. The kernel is blind to diquarks a priori, but it self-arranges itself in blocks that reflect the spin flavor structure that corresponds to these diquark objects. What does lattice have to say? A good deal, and you can read that about that in here. Lattice has provided semi-quantitative information on these correlations, on their masses, listed here, and confirmed the types of scales that are used in all types of models, sophisticated and simple, using continuum Schwinger function methods. And there are theory predictions for unambiguous measurable signals of these diquark correlations. A simple one, people are exploring what tetraquarks and pentaquarks, how they might be described if you used diquark substructure. And then there are things such as zeros in form factors, the Q-squared dependence of nucleon to resonance transition form factors, structure functions, direct dependence, and other deep inelastic scattering observables, which can be understood in terms of diquark structure. So there's a whole array of predictions that can be tested and are being tested in modern experiments. Before I go on, I'd like to pick up that notion I said before about neutron or nucleon to resonance transitions. For 100 years, we've been working on the proton, but the ground state proton is not enough. Studying the ground state of the hydrogen atom did not give us QED. So studies of the proton alone cannot reveal everything there is to know about QCD, especially if QCD is truly the theory of the strong interaction. We have modern facilities and planned facilities that can provide really extraordinary opportunities to move beyond this 100-year focus on the proton or neutron. And our store of nature of information will be so much richer if we can get our hands on this knowledge of the proton's excited states, the delta resonance excited states. We now have the capacity through the Faddeev equation to look at the structure of all these baryons. One example is shown here. This is a delta resonance, the first positive parity excited state. Actually, that's wrong. It should be a 3/2 minus there. This is the first negative parity excited state showing a P wave structure in the bound state, which is similar to quark models, but also there's a much richer angular momentum structure. And these things can be measured, charted in electroexcitation of resonances, which is something which the class collaboration is doing at JLab. So let's look at one type of physics that we can do and explain in terms of diquarks. That's deep inelastic scattering. We have a neutron and a proton, and the ratio of their structure functions at large X is a very keen discriminator between competing pictures of proton structure. Suppose, as was done 40 years ago, that only a scalar diquark exists in the proton, no axial vector. Then this ratio will be 1/4. The other extreme is to suppose that there are no correlations in the proton wave function, just an SU4 spin flavor wave function. Then the ratio is 2/3. Experiments have been trying to deliver reliable data on this for 50 years. Typically, people have used a deuteron, but there are difficulties in the nuclear physics description of the deuteron. Following a 10-year effort, the Marathon collaboration developed the capacity to use a tritium target at JLab, and that's delivered precise results on this ratio that stretch right out to about 0.85x in XB. This is the new data for the ratio. We have analyzed that data using the Schlesinger point method to see just what objective information it contains. It delivers a model-independent ratio. We don't actually refer to QCD or any other model for this. We simply look at the data and ask the question, conceivably, what does one extract from this information? And these are the results for the structure function ratio and turning that into the ratio of U quarks or D quarks in the proton to U quarks in the proton. And you see the answer for this ratio is 0.2, 0.25, and that's well above zero. And looking at the uncertainty estimate that we can place on here unambiguously, it means that scalar diquark models are disfavored at the point of 1 in 7 million. This is the scalar diquark only picture, and this is where we sit today based on combining the marathon data with another recent analysis that includes a whole array of deep elastic scattering data on heavy nuclei, and it removes the effect of short-range correlations. So we now have a benchmark against which all pictures of nucleon structure can be measured in future. I highlighted before that we've spent a lot of time and effort on studying proton structure. And we're trying to understand pion structure. What we would like to know is most simply, what are the differences between a proton seeded by 3 valence quarks and a pion seeded by a U quark and an anti-D quark? They have the valence degrees of freedom, but also all this C and glue inside of them. The question of the similarity and difference between the proton and the pion has particular resonance today as we seek to understand emergent hadron mass. We have many macroscopic differences, and we'd like to see how these things are expressed in microscopic structural features of these two very basic bound states. I sketched the Faddeev equation approach to proton structure. The analog is the pion being studied by the beta-Selpert equation. And these two things together in the continuum have been used recently to make predictions for the distributions of C, gluons, and valence quarks inside the proton and pion. What one can say, and this comes from QCD, is that on the valence quark domain, there's a scale. It's less than the proton mass. And then that scale, the valence quarks in the proton have a distribution function that behaves as 1 minus x to the power 3. And the pion has a valence d bar and a valence u distribution that behave as 1 minus x to the power 2. And these are hard predictions from QCD. As the scale increases above zeta h, these numbers increase. Just looking at the evolution equations, it's obvious that the gluon distribution functions have a power that's at least 1 unit larger, and C distribution functions have a power that's at least 2 units larger than these in each different case. The argument can also be reversed. If at large x, the glu or C distribution function exponent is smaller than that of the valence degree of freedom, then it's also smaller at lower scales. And by definition, a valence degree of freedom is the object with the highest, the lowest exponent. And that brings us to a conundrum, because we have modern analyses of proton deep elastic scattering, Drell-Yan, related effects. And they produce fits with the role of glue and valence quarks reversed. There are fits in which the valence distribution of the quark, so-called, has a power of 3, but the gluon distribution has a power less than 2. And in those terms, the glue is actually the valence degree of freedom, not the quark. And that means we have to do better. And on top of that, we have no simultaneous global fits to the proton and pion data simultaneously. That's in part because pion data is scarce. And we really have a problem. Existing approaches are not likely to yield definitive answers for the structure of the proton and the pion unless we implement the tight QCD constraints on the fits. The continuum predictions are consistent with the QCD constraints. And at the Hadron scale, they give us a very well-defined set of momentum fractions. At this valence scale, and this is the special feature of the continuum approach, is that you can define the Hadron scale unambiguously, and you can say that at this scale, the valence degrees of freedom carry all of the momentum. What you'll see, very specially, is that the pion distribution in the valence region is much more dilated. Pion is green, U quark in the proton is red, D quark in the proton is blue. They are much more compressed compared to the pion. See also that the U distribution and the D distribution are not the same. So it's U is not just 2 times D. The final conclusion is that the pion's distribution function is the most dilated in nature. This is perhaps obvious, or the beginnings of that is obvious, in the fact that the pion distribution has a power 2 and the proton valence distributions have a power 3. But there's more to it than that. This broadening also owes to emergent hadron mass. The fact that this relationship between the quark mass function and the pion beta subfield amplitude is so strong. So these effects amplify this incipient difference because of these powers. As we mentioned before, lattice simulations are beginning to reach the point where they can produce X-dependent results for distribution functions. In the proton case, they're not able to produce distribution functions pointwise for the U and D independently. That's because of the problem of so-called disconnected diagrams. They get in the way, they make a noisy signal, but they don't contribute to such isovector differences. So we have quite good lattice results for U minus D. The gray is the lattice, the purple is the continuum. So again, for the first time we see 2 completely different approaches to the problem of hadron structure, producing the same result for a measurable quantity. This is good agreement. They're both going to get better, but right now we see where both approaches are on the right track. This array of predictions here is telling us more. That the glue distribution in the pion is broader, is more dilated than that in the proton. The same for the light quark C, and the same for the heavy quark C. Glue, D and U quark C, S and C in the pion and the proton. These outcomes are measurable expressions of EHM, and we'll be able to test that again with the modern generation of experiments. A high-profile experiment was completed recently. The work was published in Nature after a long battle with referees, and I've listed the data here. This controversy began a long time ago, 30 years, but now we see that the ratio of D quarks to U quarks in the proton is not 1. There is an antimatter asymmetry inside the proton. The Gottfried sum rule gives us this difference between D bar and U bar. The continuum prediction is given here, and that matches the most recent result from global fits. We notice the bounds on this, they're not 0 and 1. What happens as X goes to 0 is very important. This can only be a finite integral if any divergence in U bar matches that in D bar. X goes to 1 doesn't matter, but every different fit gives you a different small x behavior. So extrapolations to X goes to 0 are very sensitive. The continuum prediction gives you a fixed result for that, and that can be tested. And this is taking us back to the ratio of D quarks and U quarks in the proton. I mentioned earlier that there are axial vector diquarks and scalar diquarks in the proton wave function. And that ratio is a measure of emergent hadron mass. What I'm illustrating here is the contribution of scalar diquarks and axial vector diquarks to the proton wave function normalization. The scalar diquark is dominant, but there's a big axial vector term and a strong scalar axial vector interference term, so that finally, the axial vector component of the proton wave function is responsible for 40% of the normalization. Because we can now compute the X dependence of the valence quarks and the C quark distributions inside the proton, we can compute this ratio of structure functions for the neutron and the proton and compare it with the marathon data, which is here given in gold. The earlier experiment, bonus, was done on the deuteron. you see the errors get very large as you get to large X, and they stop at 0.6. They're consistent with marathon, but with larger errors. Because marathon used tritium or the triton and helium-3, they were able to explore, minimize those uncertainties. The prediction agrees precisely with the marathon data and takes that into the infrared, where the answer will finally become 1 because C quarks become dominant. And this is the scalar Diquark only point again. If only this scalar Diquark produced the proton normalization, then this ratio would be 0 at X equals 1. But the data, our previous analysis, model independent, and our current calculations show the probability of a scalar Diquark only proton is 1 in 7 million. So the continuum string function methods have delivered the first ever unified prediction for all proton and pion DFs, valence, glue, and a 4-flavor separated C. What we've learned is that mesons and baryons that share the same flavor structure, the same family type of flavor structure, will have a light from momentum fraction at the Hadron scale, which is the same. That's what's illustrated here. At the Hadron scale, the gluon fraction of momentum in the pion is the same as the gluon fraction in the proton. Summing the valence-quark fractions in the pion, I get the same as the valence-quark fractions in the proton, and the same for the C quarks, sum of U and D bar in the pion, U and D in the proton, S, C, and so forth. The higher moments are different, and that's the key. So the smoking gun for emergent hadron mass is the x-dependence of distribution functions. At any resolving scale, distribution functions in the pion are the hardest, they're the most dilated. These continuum predictions are consistent with QCD constraints on both low and high X scaling behavior. Low X is important, as I highlighted in connection with the Gottfried sum rule. Many fits produce a gluon distribution at small x, which is finite. Contemporary ladder simulations, which cannot adequately deal with low X behavior, are also producing a finite result for the gluon exponent at small x. But QCD continuum predictions give you a gluon distribution that diverges at small x, a power like 1 over the square root of x. The problem we have is that existing global fits ignore these QCD constraints, so they fail to deliver realistic distribution functions even from the abundant proton data. And since meson data is almost non-existent, we have very controversial results from those fits. So the suggestion is very strongly that we should impose QCD constraints on future phenomenological fits so that we can draw reliable pictures of hadron structure. And this will be extremely important if we want to understand differences between Nambu-Goldstone bosons and what might seem to be less complex hadrons, such as the proton. There are an array of documents that spell out how we can explore meson structure. To gather that data, that will make it possible for us to finally produce global fits that unify both proton and pion data. They rely on the AMBER facility, on the electron ion collider, and on JLab, and on electron ion collider in China. So I can wrap up now. I've argued that QCD is unique amongst known fundamental theories of natural phenomena. The degrees of freedom used to express the scale-free Lagrangian are not directly observable. We have massless gauge bosons, and they become massive, and we don't do anything to interfere with that, to make it happen. We don't add some Higgs-like object to make gluons massive. They just do it by themselves. The gluon mass is a reality. Continuum and lattice agree on that. It provides for an infrared completion of QCD through the appearance of a running coupling that saturates infrared momenta and is everywhere finite. We have massless fermions that become massive, and that makes us produce massive baryons and simultaneously massless mesons. These are emergent features of QCD, and they're expressed in every strong interaction observable. And as I've sketched, we can also use this array of experiments to expose the interference between emergent hadron mass and nature's other source of mass generation. That's the Higgs boson. And this is a special time because with the development of technology, we are now capable of building facilities that can produce what are effectively meson targets. So we can then use these facilities to validate these concepts and perhaps prove that QCD is the first well-defined four-dimensional quantum field theory that we've ever contemplated. And that may open doors that lead us very far beyond the standard model. Next steps, lots more to do. We have a workshop coming up. We just finished this workshop on the EICC conceptual design report. We have a CERN tele-workshop coming up in the middle of May. We have Fun QCD in Valencia in June. We have a mixed phase workshop, face-to-face and remote at ECT Star in September, and the BARYON conference in November. Here in Nanjing, we will have workshops, but we have COVID still to worry about and other well-known international developments which are preventing us from making any concrete plans. So with that, I'll stop. And thank you very much for tuning in today and listening to what I had to say. Thank you.
Thank you, Greg, for a lovely talk. The floor is now open for questions.
David has a question, Konstantinos.
May I say hello?
Yeah, I had to unmute. Okay, thank you very much. It was an excellent talk. It was a pleasure to see such a talk again. I actually wanted to applaud, but okay, as now my hand is open, I can also ask a question. I was very much interested in this remark about the scalar Diquark and its role. Can you please elucidate how you get this number of 1 in 7 million for the relative unimportance of the scalar Diquark? Because as you might know, I am interested in quark matter, and I point out that scalar Diquarks are very important for the phase structure of QCD and for compact stars, where scalar Diquark condensation plays a tremendous role for where actually the chiral phase transition is located in terms of density. So therefore, how can I understand this number? Can you please elucidate?
Okay, David, hello.
Hi.
I've shown a picture here again of the marathon data.
Yes.
And these bands are what you obtain from the data using the function form independent analysis procedure, which we call the Schlesinger point method. And what this method gives you a way of saying just objectively what information is contained in the data. It describes the data perfectly on the domain where the data exists, and it provides a well-defined extrapolation to the point x equals 1 with well-defined uncertainties. And there's no model dependence in this. This is just the information contained in the data. And you can see this ratio dV over UV in the proton is 0.25, 0.25, shall we say. And there's an uncertainty band. And the scalar Diquark only picture lies way down here. And say, taking into account the statement about what standard deviations mean, then the difference between 0 and 0.22 corresponds to a probability that a scalar Diquark model might be viable of just 1 in 7 million. So this is the objective content of the marathon data. Before marathon data, we couldn't have said anything like this because the bonus data, as I illustrated in another transparency, maybe here, no, still going back, sorry, there. This is the bonus data. See how that data curves down here? And people were using the bonus data, fitting the bonus data, to get down to a point where dV over UV was approximately 0, 0.09 plus or minus a bit. But now we see with the marathon result that that's not tenable. You really must have a result which is up around 0.22, 0.25 for the valence dV over UV ratio. So that means the proton does contain activated Diquarks, these quantities here. On the theory side, no picture of the proton that preserves Poincare covariance can possibly lead you to a picture of the proton with just a scalar Diquark. If I take the 3-body Faddeev equation approach, then there are 128 different invariant amplitudes that are necessary to describe the proton. And a very, very, very small fraction of those involve just a scalar diquark-like correlation. So just Poincare covariance tells you that you're going to have an active diquark. The amount is determined by dynamics, and you can see here what modern pictures of the proton produce. So I hope there's scope for active diquarks in the pictures of finite density that you're exploring, David.
Thank you very much, Greg, for the elucidation.
May I say?
Please go ahead.
Please go ahead.
My microphone is open. May I say? I have some comments. I would like to pay your attention all to graphene, in which the strong interaction is main reason to acquisition of mass in massless fermions. Thank you.
Okay, thank you for the suggestion. You're correct, of course. The dynamics is at basic level different, but of course, the whole notion of the formation of correlations in strong interacting many-body systems is uniform across many fields of science. And that's one of the things that we emphasize when we speak more generally about these notions of diquark correlations. Thank you.
Yeah, so as you know, Craig, my interest is in finite temperature. And so very loosely speaking, as the temperature goes up, there is a deconfinement and we have a quark-gluon plasma. So in your description, what is the main driver state? So in other words, is it the gluon mass function or is it something else?
I think the simplest expression of restoration of chiral symmetry is passed through the dressed quark mass function. That mass function, as you increase the temperature, remains stable at low temperatures, but suddenly, as you approach the transition boundary, drops away towards zero. And so you have a chiral condensate that vanishes or becomes very small at that point. And that will feed back into the gluon sector because massless fermions are very effective at screening. So that will very likely affect the character of the gluon mass function. There are people who have studied that. I'm not one of them, so I can't tell you much more about it than that. My studies have been on the quark mass function itself. So the expression is primarily there. The feedback into the gauge sector, I can't tell you much more about.
Okay, thanks.
Victor, go ahead.
Craig, thank you very much for really inspiring talk on strong QCD physics with a common framework both in Meson and baryon sector, addressing emergence of Hadron mass. My comment and question is, could you please show momentum dependence of dressed quark mass for quark of different flavors?
Let's see. Getting close, Victor. There we go.
No, here it is. If we would live in toy world of perturbative QCD, then interaction of the quark of different flavor should be flavor independent. This plot clearly showed that this is not the case. The dominant part of dressed quark masses for light quark is coming from quark interaction. Instead, for heavy quark, the major part of their masses is coming from Higgs mechanism. My question is, whether studies of flavor dependence in Hadron mass generation, clearly shown in this plot, be the major motivation for the future studies of spectrum and structure of Hadron with heavy quark, heavier than U and D quark, in the future facility of high energy and luminosity.
Well, the answer is simply yes. The strange quark is accessible at all facilities, and very little is known about the spectrum of systems containing strange quarks. You are well aware that the so-called missing resonance problem is much stronger in the strange quark sector. We don't know much about the spectrum of strange quark carrying mesons, and the AMBER project has one strong arm devoted to charting the spectrum of mesons involving strange quarks. So yes, we ought to focus on systems with strangeness. Your point is also well taken that when you have strangeness, you have a way of exposing the interference between emergent hadron mass and the Higgs mechanism. And that's a very valuable tool. There are many ways of doing it. Electroweak processes, semi-electronic decays are one way of doing it, but the spectrum and the strong transitions between hadrons involving strangeness are another way. So I think that's a good motivation for the type of experiments that you just described.
Craig, as you mentioned, S-quark are accessible even now in 12 GeV era. We are thinking in Jefferson Web about extension of our program beyond 12 GeV era, and maybe C-quark will be accessible in this experiment, both for the spectrum and for the structure.
And charm quarks, there are many things you can do. What's interesting about Jabe Psi and the eta C is the different feedback or interference between the Higgs mechanism in both systems, because the eta C is a pseudoscalar meson and the Jabe Psi is a vector. So they have different footprints of interference between EHM and Higgs boson effects. So studying those systems can provide us with new information on how the two mass generating mechanisms work with one another to make the spectrum and the interactions that we see.
Thank you.
Dionysius, ask your question.
Hello. So I wanted to ask, not of course by giving many details, but could you say how you calculate the Parton distribution functions, for example, in the either in the Proton or in the Pion? I mean, what is the basic ingredients that you need to calculate those?
Yes, certainly. The basic ingredient is a matrix element, and the matrix element is an endpoint Schwinger function, and you must develop a truncation scheme or a calculation scheme for the computation of that Schwinger function. Lattice uses one set of methods, and we in the continuum use a different set of methods. So we write down the Schwinger function, we develop a symmetry-preserving truncation for that Schwinger function, and then we input the dressed quarks, the dressed gluons that you've seen here today to produce an answer for what the distribution function is therefrom. Is that simple and clear enough?
Yeah, so these are calculated at various values of Q square, which I think you called zeta, right? The zeta was
Right,
the Q
yes.
square.
We calculate these at the hadron scale. There's a particular statement that we make, and we're very firm on this. These continuum calculations define the distribution functions at the scale zeta h, which is less than the proton mass. And from that point on, the process-independent charge then serves the role of the kernel to define the evolution equations. So we take the distribution functions we compute at the hadron scale, and we use one-loop evolution and the process-independent charge to give the distribution function at any other scale. And that's part of the calculation. In a sense, we then reinterpret the process-independent charge as a process-dependent charge following the pattern suggested by Grunberg when he invented the notion of process-dependent charges. And that's been extraordinarily effective. It's provided us with a way of unifying these pion, kaon, and proton distribution functions that I didn't think was possible just 2 or 3 years ago. So this is a change in perspective that is important to explore. And we have an array or a number of recent publications which presents that picture and explores the consequences. And I think Daniele can point you to some of those if you're truly interested.
Thanks.
Are there any more questions? If not, I would like to thank Greg again for a lovely talk. And
Well, thank you all very much.